Okay, I think we can begin. Good afternoon, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Network Intelligence at the Robert Bosch Center for Cyber-Physical Systems, ISC. Today's talk is by Dr. Anup Thomas, and he'll be speaking on coded gradient aggregation. Dr. Anup Thomas received his BTech degree in Electronics and Telecommunication Engineering from College of Engineering, Kerala University, Trivandrum in 2008, and ME and PhD degrees from the Department of Electrical Communication Engineering, IISc Bangalore in 2013 and 2018, respectively. He is currently an assistant professor with the School of Electrical Sciences, IIT Bhubaneswar. His primary research interests include network coding, index coding, coded caching, and gradient coding. Before we move on to the talk, we'd like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I'll be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Dr. Anup or type them in the chat box and we'll moderate it with him. Over to you, Dr. Anup.
Yeah, thank you, Nishad, for the introduction. Am I audible and my slides are visible? Can somebody confirm?
Yes.
Okay, thank you. Yeah. So good evening to all, and welcome to my talk on coded gradient aggregation. And once again, thank you for inviting me to give a talk on this CNI Network Seminar Series. And it is good to be back giving a talk at IISc Bangalore, even though it is in an online mode. Last time I gave the talk, it was my PhD thesis defense. So it ended well. So I hope this will also go very good. Okay, and so I have roughly planned for a 40-45 minutes talk. So whenever you have a question, please feel free to just unmute yourself and raise a question. That is it. So let me start with a brief outline of the talk. So the talk is, we'll start with a review on gradient descent, which I believe everybody knows, but still we will give a quick review. And then we will move on to distributed gradient descent, how these things are done in a distributed manner. The focus of the talk is mostly in a hierarchical setup, in which in addition to the edge nodes, there are some intermediate nodes in the network, which will assist in communication of these gradients between the edge nodes and the master node. And it is observed that, or we can see that there are, by using some coding schemes, we can control or adjust the communication costs involved in this transmission of gradients. And in particular, we will be dealing with three coding schemes. One is called as aligned repetition coding, where we use some variation of a repetition code, and aligned MDS codes MDS coding where we use MDS codes, and finally a pyramid scheme where we use pyramid codes for this gradient aggregation. And I will conclude the talk with some future directions and maybe posing some challenges or unknown facts, etc., so that interested people can take it up. So let us start with a very quick review of gradient descent. Yeah. So sorry. Yeah. So we have a data set here. Capital D is our data set, and it has D data points. So x1, x2, etc. till xd. These are the data, and y1s are some values. The objective is of a gradient descent algorithm, which is a very commonly used optimization algorithm, is to minimize some cost function, a differentiable cost function, and to minimize any loss function. So here the loss function is indicated by this L of theta comma x comma y, which has to be computed across all the data points belonging to the data set. To minimize this loss function, what is typically done is you compute the gradient, and then you use this gradient to update your parameters. So here theta represents the parameters, and in each iteration you update the parameters theta by using the computed gradient. Okay, so this is an iterative algorithm, so this has to be going on in multiple steps, and at each step you have to compute this gradient over the entire data set, and you update the parameter, and it goes on. If the function is differentiable, etc., it converges eventually. But the important step is that this gradient needs to be computed at each step over the entire data set. So we are dealing with synchronous, we are considering synchronous gradient descent for the time being. And so the gradient has to be computed across the full data set. So let us look at why we need this distributed or parallel gradient descent is that because currently we are living in a world of big data and the data set is so huge and it is very difficult to have this entire data at one particular location. Also, it is very difficult to make one particular machine or server to work on this full data. Similarly, the parameter size also is very, very huge. In many data sets, the parameter size is huge. And this is also takes, in fact, the parameter size actually determines the size of your gradient vector. So having massive parameter size incurs a lot of communication costs, which actually slows up your process it really slows up your process. And we have a lot of computation resources at every level, at our edge nodes, at our intermediate nodes, in the master node, everywhere computation resources are available. And the objective is to make use of these computation resources so that we can fasten up the process. And one of the most important point is that the data itself will be very, very distributed. So to get the data to a central location, that involves so much cost. So all of our mobiles are generating a lot of data. If anybody is wearing a wearable device like what do you call it, health monitors or anything, that is generating a lot of data. And to centralize this data, to transmit the actual data, it is taking a lot of bandwidth and other constraints. So yeah, also the last point is privacy constraints. Everybody, most of us prefer the data to be in our device. It need not be sent to a central server, or it need not be taken out of our device for further processing. However, at the same time, we also demand very high quality services like very good face recognition features or very good features which will actually enhance our applications. So we want to get the benefits out of this global learning, etc. But at the same time, we don't want to share our data to the central server or main node who can process this data. So Google was aware of this problem long back, and they came up with a solution called as federated learning in 2017 itself. I think it was rolled out in 2019. So the idea is that you will have a local data, and using the local data, you will train your own models. Okay, and this models are sent to the central server, who actually accumulates all the local updates and then create a global update and push that global update back to the local nodes. So it's a very simple idea, but it is very effective. And this was used in Google Keyboard particularly. So in Google Keyboard, what is the advantage is that, so suppose like if some new movie came out and there are some nice punch dialogues, etc. Even if you haven't used that, if many of your friends have seen and started typing that, so that will come as your prediction. So that sort of, depending upon how the others use, some sort of new prediction actually comes to you also. So this is federated learning, and now it is being applied in other applications like Google Lens. Also, they use that, and they are potentially looking for many applications. But again, the main idea is that the data is stored in only in your mobile, and only the updates are being transferred up to the central node, and similarly, an update is coming from the central node to the local node. The actual data always remains at the local nodes. So similarly, we model slightly different. We are considering gradient descent. So here, the gradients or the data set is at different edge nodes. So here we have different data sets: D1, D2, D3, etc., Dn. One advantage is that these data sets need not be of any uniform size, because it is locally generated. So you really do not have any control of the size of the data set. And you assume that these are anyway distributed. So you assume that the nodes can compute the gradient across these data sets. So what it does is it computes the gradients G1, G2, etc., Gn, corresponding to the data set D1, D2, D3, etc., Dn. And these gradients are being sent to the central server. And the central server, what it does is it aggregates these gradients, takes the sum of all the gradients, and then it updates the parameters. And these parameters are now pushed back to the edge node. So here I have illustrated this edge nodes as mobiles, but it need not be like mobiles. It can be any devices, like any IoT devices, which can do a very basic processing. So from this, so this is the idea. So you have data available at your edge nodes. You compute the gradients. You transmit the gradients to the master, who does the aggregation, and then you send back this updated parameter back to the edge nodes, so that the models or this gradient descent continues to the next iteration. Again, you compute the gradient with the new parameters, and then this iterative process continues. So one of the problems is that these edge nodes may not be available continuously, because they may be only intermittent in nature. They are intermittent in nature. Another thing is that they may be power constrained or bandwidth constrained. Okay, and this is particularly more prominent in IoT applications. So in order to aid these helper nodes in this transmission of these big gradient vectors, normally in the network there are some helper nodes associated to edge nodes. So this helper nodes is assumed to have a reliable connection with the master node, and the edge nodes will communicate to the helper nodes the local gradient, and these helper nodes will actually communicate the local gradients back to the master after doing some possible aggregation. So we will learn about what is the aggregation that the helper nodes will do, and that is the focus. So this leads us to our system model, which was actually came up in this paper, hierarchical coded gradient aggregation for learning at the edge in 2020 ISIT. So there are any edge nodes. So there are arbitrary number of edge nodes, each having a local data set D1, D2, etc., Dne, and it can compute its own gradient G1, G2, Gne. And this G1, G2, Gne is transmitted to the helper nodes. We have NH helper nodes, again an arbitrary number. Typically, this NH will be around logarithm of Ne. That is one typical model. And then these helper nodes are connected to the master node via an error-free link. So one of the things that edge node, what is one of the things that edge node can do is edge node can transmit this G1 to all the helper nodes. Okay, so we make an assumption that the edge nodes have an access to all the helper nodes. That is the initial assumption, and then it can transmit to all the helper nodes same G1. But the catch is that since these edge nodes are like intermittent, or since they have some power constraint, etc., we assume that the transmissions between edge nodes and helper nodes are not reliable. So the assumption that we make is that there are at most S erasures between each edge node and each and the helper nodes. So if an edge node transmits NH transmissions, makes NH transmissions, we assume that S of them are not, maybe at most S does not reach the intended target here, which is the helper nodes. Okay, so that is a model. And so what each edge node can do is it can actually transmit G1 in to all the helper nodes, but then you are actually doing extra. You are transmitting a lot of content which may not be desirable because your edge nodes are already power constrained. So then what it can do is it can split this gradient vector into k parts. K is we will explain what is k, but it can split into k, which is an arbitrary number, and then it can use a code, a client code, we refer it to as a client code, to convert this k parts into an NH parts. And in each of these, it will transmit to each helper node, it will transmit one symbol of that coded version of the gradient. So if you have a generator matrix G for the client code, then G, you can multiply the splitted gradient with the generator matrix to obtain CI1, CI2, etc., CINH, which is being transmitted to each of the helper node by the edge node I. So here I have explained for edge node I. So if you look at E1, C11 will go to H1, C12 will go to H2, C1NH will go to NH, like that it goes. So that is the idea. So the advantage of using this client code is that you can actually reduce the you will get some control over the amount of transmission cost that you are incurring at edge nodes. Similarly, you will get more control over the amount of transmission cost that you are incurring at the helper nodes. Now, what the helper nodes do is that once it receives these transmissions, it can identify whether erasures are happened. So it constructs an erasure pattern and it transmits the erasure pattern to the master. So the erasure pattern is like only binary, like it is like 1 or 0, whether an erasure has happened. So it is not transmitting any big data. It is transmitting only whether an erasure has happened or not. So the master can construct the full erasure pattern, and then it can ask the helper nodes to transmit these gradients after possible aggregation. Again, aggregation I will explain. But the master can do this, and it can ask the helpers to transmit, how to transmit or what to transmit after possible aggregation. So that is
Question, the alphabet over which you're operating is real valued, or is it a binary or some other discrete alphabet?
So it is not real valued, it is some finite field. I agree that the gradients are like real valued generally, but then we have to do some quantization, and then there is another separate study. I am referring it to there in the end actually. So currently we are assuming that the alphabet is a finite field character, but a quantization has to be done.
Thank you.
Thank you. Thank you for the question. So yeah, so let's continue. Yeah, so clearly we can see that there are two costs. That is, one is the communication between edge, two types of communication. One is the communication between edge and helper nodes, and there is a communication between helper and master nodes. So there are two costs involved. So let me first tell the two costs. That is, one is the communication cost at the edge node. So we will denote that by CEH. So that is communication cost between edge and helper. And this actually depends upon the client code used. So if you can see, the size of each gradient vector will be p by k, and that is now being encoded into nh symbol. So nh into p by k will be the total transmission vector size, and this is normalized with your parameter to obtain CEH. Is defined like that. So CEH is nh by k. If you use a client code having dimension k, you can calculate CEH very easily. The second cost is the communication between helper and the master node. So this actually depends upon the erasure pattern. It is not what you call, it is a random value, so it changes. So what we define CHM is the average over all erasure patterns. So here omega of s denotes the set of all erasure patterns. So and we have assumed that all erasure patterns are equally likely, so 1 by cardinality of omega of s. And what is the amount of size of the vectors that is transmitted for each erasure pattern epsilon and for across all helper nodes. So you add up the transmissions across all helper nodes for all erasure patterns, and then you average it out. So here this mj epsilon indicates the size of the transmissions, or the number of transmissions made by the helper nodes, j for an erasure pattern epsilon. The important thing is that it is an average and it depends upon the erasure pattern. So we average it out to find the value of CHM. And the quantities that we are particularly interested is in these two quantities, CEH and CHM, how to characterize that. And in particular, whether we can get a handle on these two quantities, CEH star and CHM star, which are defined as the infimum of CEH over all possible achievable CEH CHM pairs. Similarly, CHM star is defined as the infimum over all achievable rates of CHM. So these are the two quantities of interest. So first, let us see the first scheme. So that is an aligned repetition coding scheme. Yeah. So here what it does is very simple. So it actually takes the gradient and splits into s+1 parts. So I'm making an assumption that nh is divisible by s+1. So k you can actually compute, it's an integer value. So immediately you can find CEH. So CEH will be equal to s+1 because nh by k is the formula for that. Then the next important thing is, since each gradient is split into s+1 parts, okay, that is k is equal to nh by s+1 parts, you can actually put this gradient into s+1 locations. And we are considering a setting where only s stragglers are there. So there is a guarantee that at least one helper node receives your your gradient, that part of the gradient vector. So that ensures resiliency. This can be easily understood by a small example. So here I have a small example. So this is for n equal to 4, nh equal to 8, and s equal to 3. So you have 8 helper nodes. So typically NE will be very large, but for example purposes, I have kept it to be 4. Okay, so typically NE will be around like 64,000, etc. But for example purposes, I have kept it small. So the idea is that if you observe, there are 3 erasures at each row. That is the erasures that are faced by the edge nodes. And if you observe H3 is not experiencing any erasure. So what can H3 do? It can just add up all these terms, and then it can transmit the aggregated vector to the master. So that is what H3 will do. So if you look at H3, you can add up all the gradients. These are like first part, maybe gradient is divided into 2 parts for this particular example because S is 3. So 8 by S plus 1 will be equal to 2. So this H3 can transmit an aggregated gradient and it can send to the master. So master will receive one part of the aggregated gradient. The second factor is that if you look at H6, H6 can aggregate 3 and H8 can send the remaining last what you call one part of the gradient that is left. So once all these messages are being transmitted, so here in this case 3 transmissions are being made. Once all these 3 transmissions are being made, the master will be able to reconstruct the full gradient. So we have the communication load as 3 into P by K by P. So that P gets cancelled out. So it will be 3 by 2 for this particular example. So
yeah, Anup, just one question. So
yes.
Like, yeah, for H8 assume that like G22 was not erased, for example, right? I mean, in that case, what would happen? I mean, in that case, I mean, it's there is overlap between the sums, right?
What happened?
I mean, so suppose for H2, assume that G22 was not erased.
Yes.
So, and like, I mean, in that case, I mean, there could be an overlap between the sums, right?
So the master has control over what the transmissions are being made by the helper node. So it can clearly instruct what to transmit.
Oh, okay. There's a feedback.
That is the idea. So the reason behind that is, again, the thing is that during the initial communication, you are only sending a binary data, whereas you can think that these gradients are actually large size parameter vectors. So once you start transmitting gradients, you have to transmit big data. You can think like that. So some communication is happening that is in binary format, so that we are not focusing on. But that communication is there.
Okay. Yeah, thank you.
So here again, this is an example of how it is being shown. Like what is this is an example. So how do you identify this H3, H6, H8? There are a couple of algorithms. One is you can just look at which helper node as the first. For example, if you are looking at G11, you identify which is the first helper node having G11 and ask that particular helper node to transmit. Another thing is this problem can be converted into a set cover problem. Okay, so this set cover problem, and you can use a greedy algorithm to solve that. It is to find the optimal solution is very difficult again for CHM, but you can have greedy approaches to find suboptimal solutions. So that is one word. So CHM exact value is not known, but what we can interestingly observe is 2 things. First is the most favorable scenario is having a particular helper node which has all the gradients, so that your transmissions are significantly reduced. So that is the minimum communication load occurs when erasure patterns align, and this happens. And if you have, you need only minimum number of helper nodes. So the minimum number of helper nodes should be at least 2. So under that setting, so CHM will be 2 into, so K, general case will be K into P by K into 1 by P. So that will be greater than or equal to 1. Okay, so it's a very simple bound. And the worst case is when all the helper nodes has to transmit. So we have NH helper nodes. All of them has to transmit at least one P by K length vector. And then it will be NH by K, which will be equal to S plus 1. So this is the worst case of communication load. Since CHM worst is like S plus 1, obviously the optimal will be less than or equal to S plus 1, and we have some handle on the bound of CHM. So it will be greater than 1 and it will be less than or equal to S plus 1. So that is about aligned repetition coding. Very simple scheme, but still we will get some idea about CHM star in general. But the problem with this aligned repetition coding is that you are actually making the edge nodes transmit more. Because G11 is being transmitted at least 4 times and G12 is being transmitted at least 4 times. So you are making a lot of transmissions from the edge side. So it is CH value is typically a little bit high. Now we'll move on to the next scheme wherein which we use MDS codes. So in MDS codes, the client code used is of dimension NH minus S. So why we use NH minus S is because your length of the code is NH and dimension is K. So the erasure, the minimum distance of the code will be N minus K plus 1. So that is NH minus S plus 1. So you will have S plus 1 as your minimum distance. And we know that S plus 1, if the minimum distance, then you'll be able to correct S erasures. So that is our idea. So CH for this is again NH by NH minus S. So that is NH by K. Let us look at how the aggregation happens. So here is another possible illustration of an erasure pattern. Here I have taken NE equal to 10. Okay. So let us look at the first 3 rows. Okay. If you look at the first 3 rows carefully, you can see that the erasure patterns are aligned. Okay. So every second is erased, every fourth is erased, and every, I think, eighth is also erased. So once these erasure patterns are aligned, we can do something. We can aggregate this and transmit. So helper 1 will aggregate these 3 and transmit. Helper 3 will also aggregate these 3 and transmit. Like that, it can aggregate and transmit. The reason because why we can do that is because we are not interested, or I mean, master is not interested in computing each of the local gradients. It is only interested in computing the sum. So you can always do aggregation and transmit it. So you are effectively decoding to a sum of the code words, and you need 5 bits or 5 transmitted symbols for the decoding to happen. So you have to transmit 5 symbols of the sum of code word, which is a sum of these 3 code words. Yeah. So yeah, I have briefly written down what I have just explained. But again, the important thing to remember is that you are only interested in the sum of the code words, and therefore you can do this possible aggregation. Okay, so that is the idea behind CHM. So again, another thing that we have to understand is that what is the important thing is that erasures should align. So there are multiple possibilities. There are many possibilities in which erasures can align. So what we consider is the alignment in which offers us maximum gain. So we will look, or the master node will actually look for the largest set of matching rows in the failure table, and corresponding to the largest set of matching rows, it will ask the helper nodes to aggregate that largest set and then transmit. So if let us denote the largest let us denote the cardinality of the largest set by this capital letter M, then for these M rows, they will aggregate and transmit only like K symbols, each of size P by K. Again, it is normalized by P, so you will get 1. So for this M rows, you will have only the load incurred will be only 1. And for the remaining rows, we are not doing any aggregation, even though sometimes you will be able to do the aggregation. At least for this particular aggregation strategy, we are not doing any aggregation. For the remaining rows, we need to transmit, for each of the row, we need to transmit K information symbols, which is required by the master to decode, because you need to make K transmissions so that the master can decode using the MDS property. So effectively, you have NE minus M remaining rows, and there will be K transmissions made, each of size P by K. Again, normalizing with 1 by P, you will get NE minus M. So overall, you will get NE minus M, and plus 1 is your load, is your communication load. But again, CHM is a random quantity, and this M is a random variable. It depends upon the observed erasure pattern. What is the maximum value of the maximum matching set, size of the maximum matching set? It depends upon the observed erasure pattern. So you have to do an expectation of this quantity over all possible erasure patterns, and then we will obtain the expression for CHM. That is NE minus expectation of M plus 1. So this is the CHM for an MDS coding scheme. So I have explained 2 schemes. So in 2 schemes, that is called as ARC scheme and AMC scheme. So here is just a quick summary of the result. So CH will be S plus 1 for ARC scheme, and we also found out 2 bounds, one on CHM star, that is it will be greater than or equal to 1, and it will be less than or equal to S plus 1. And for AMC scheme, I have denoted as CH star, so I have not given a proof of optimality here, but in the paper it is clearly proved that CH star is NH by NH minus S, and CHM is NE minus expectation of M plus 1. What is interesting in these 2 schemes is that if we observe that if CH is high, and then correspondingly CHM is low, and when you reduce CH, you can see that CHM is becoming high. So there seems to be a trade-off. So that is our question: can a trade-off exist between CH and CHM? So
question.
Yes.
That expectation, what is it with respect to?
So it is
what is the
expectation
random-
of all possible erasure channels. So erasures. So you have.
But what erasure model did we assume? We just assumed that there can't be
Uniform.
more than S erasure, right? Or is it independently?
Yeah. So there are at most S erasures, and these erasures can occur anywhere uniformly.
Okay, thank you.
So it's an averaging out, at least in this model. You don't have any assumption on how the erasures are happening. So you assume that all erasure patterns are equally likely and then find it out. If you have more knowledge about erasures, maybe we have to appropriately modify. But yeah, our assumption as of now, this expectation, we are assuming that all erasures are equally likely and doing it. Okay, thank you. Thank you for the question again. Yeah, so so the question that we want to pose is whether a trade-off exists between CH and CHM. In fact, there is a scheme called as pyramid scheme, which we proposed in this year 2021 ISIT. So where we consider a pyramid code instead of MDS code. So first I will briefly describe a pyramid code. So here the client code being used. So the essential things we have is we have two things which we can change. One is the aggregation strategy, which the master does. And the second is the client code that we are using. So here we are changing the client code. So appropriately, we will modify the aggregation strategy also. So a pyramid code, again, I will illustrate it through an example. What is our strategy? So we will construct a pyramid code starting from a Reed-Solomon code. So assume that this is the generator matrix of a Reed-Solomon code. So what we do is we will consider a parity column here, and we will split this parity column into two. As shown here. So this A11, A21, and A31, A41. It is split into two: A11, A21, and A31 and A41. So you have increased the length of the code. Okay, the dimension remains unchanged. That is the important thing is that if you look at the column 1, 2, and 5, this has a local coordinate. Okay, so if I have say first symbol, second symbol, and the fifth symbol that has a local code structure, I can do some. It is actually a single parity check code. Similarly, between 3, 4, and 6 also I have a local code structure, and then there are two global parities, that is the 7 and 8. So the idea is to try and add a little more locality so that maybe we can use that and see whether does it improve or does it assist in the trade-off. That was our attempt. So just brief some notations. So the number of local codes in general is denoted by T. So in this particular example, it is 2. And the support of local codes is generally is denoted by Li. So here we have 1, 2, and 5, which is a support of first local code, and 3, 4, and 6, which is support of second local code. And dimension of each local code is denoted by KT of I. So here in this particular example, the dimension is 2 for both the local codes. In general, it need not be same. Local codes can have different dimensions, but we are taking a simple example here. And the dimension of the full code is the sum of the dimension of all local codes. And again, we desire that the minimum distance is maintained. So if you look, we want to maintain the minimum distance as 4 because we want to correct S+1 erasures. So here S is assumed to be 3 for this particular example. And we can compute the KT. Once we know what is the dimension of the pyramid code that is required, we can immediately compute what is CEH. What is more challenging is CHM and the aggregation strategy that we follow. So again, we will look at the aggregation strategy using an example. So we will take a possible erasure pattern for 10 edge nodes. Before moving on to explaining the aggregation, I want to make some definitions about the type of erasures. So erasures can be classified. So we will define two terms, that is unaffected local codes and overwhelmed local codes. So unaffected local code means if subjected to that particular erasure, if you can recover the symbols in that local code by using the elements of the local code alone, then that local code is said to be unaffected by a particular erasure pattern. Otherwise, it is said to be overwhelmed. So erasure patterns, based on this definition, we can classify erasure patterns into different types. So here the type of an erasure pattern is an ordered pair of vectors u comma v. So here u indicates the overwhelmed codes. So it is a binary vector which actually indicates the position of the overwhelmed codes, and v indicates the number of erasures in an unaffected codes. So let us understand this by seeing two examples. Yeah. So here is one erasure pattern. So if you observe this erasure pattern, there is an erasure at second position, there is an erasure at fourth position, and there is an erasure at seventh position. So if you look at the local codes, that is 1, 2, and 5, there is only one erasure. If you look at the second local code 3, 4, and 6, again there is only one erasure. So one erasure means a single parity local code can easily recover from that. So that means it is both the local codes are unaffected. So U will be 0, 0 because there is no overwhelmed codes. And V indicates the number of erasures in unaffected codes. So V will be 1, 1. So that is the idea. I have one more example. So here is an example where if you look at 3, 4, and 6, you have 2 erasures. So that means your second local code is overwhelmed, and that is why U is equal to 0, 1. And V is 1, that indicates that there is one erasure in the first local code, that is the second position. Okay. So the idea is that depending upon this erasure pattern or erasures, this can actually be classified into different types. So erasures can be classified into different types. And why we are doing this is because our aggregation strategy actually depends on the type. So depending upon the type, we will continue with the aggregation strategy. So let me explain the aggregation strategy when the under the setting that U is 0. So U is all 0. So U is an all 0 vector. That means all local codes are unaffected. So here is an example. So this all the 4 erasures satisfy this criterion. That is, all the local codes are unaffected, 0, 0, and 1, 1. So under this setting, since the local codes are unaffected, the helpers needs to transmit only the local code symbols. So it looks in local code symbols, it discards all the global symbols, and it looks for matching only within this first 6 columns. So it doesn't matter if, for example, this even if this C17 and C28, even if these erasures does not match, we can still do aggregation. So that is what it is done here. You can still perform these aggregations, and then you can ask the this can be transmitted, and the master can decode all the gradients from these transmissions. Why? Because again we are transmitting 4 symbols, and all the local codes are locally recoverable. So from this information, it will be able to decode it. Observe, there is one more thing that is to be observed. Observe that there is a E4. In E4, there are it is also of the same type. So erasures are of the same type. It is same type, but still it cannot be aggregated because there is a difference in erasure pattern in the local code symbols. So here C41, here the erasure patterns are not aligned. So that is why we are not able to aggregate. So even within a type also we cannot do the aggregation. So we have to be aware of this. So in that case, what we do is we'll just transmit the information symbols from the local codes directly, and then this can be decoded. So there are 2 steps. If the aggregation is possible, we will aggregate and transmit. If it is not possible, we will directly transmit the symbols. But again, we are looking at only a subset of the columns. We are not interested in whether the global parities erasures match. We are only interested in the subset of the columns here. So that happens when all local codes are unaffected. So I hope that is clear. Yeah. So even I have just written out what is being transmitted. So an aggregated C1j plus C2j plus C3j is being transmitted. Similarly, this if aggregation is not possible, you'll just transmit directly. So the second case is when so all local codes are unaffected is covered. So the second case is when sorry. Yeah. Okay. Yeah, so here is one more example where you have a different type. For example, U comma V. This is having a 0, 0 and 0, 1 is a type. So under this setting also, you don't have anything matching with this particular type in this particular example. So you cannot do aggregation. So you just have to transmit the information symbols. So whenever u comma v is, whenever u is 0, 0, our focus is on the local codes only. Now, the second condition is when at least one local code is overwhelmed. If one local code is overwhelmed, then our strategy changes. So here is an example. So here you can observe that there are erasures in 3 and 4. So there are 2 erasures in the second local code. So the second local code is clearly overwhelmed. And here the type is 0, 1, 1. So what we do is if the second local code is overwhelmed, then the symbols from unaffected local code is transmitted directly without any aggregation. So, so from the first local code, we will transmit the symbols without any aggregation. So that is C52, C55 is the possible that, so for example, C51 is lost. So they will transmit 2 symbols from the C52 and C55. So this is 1, 2, and 5 is the first local code. So similarly, it will transmit from the first local code. And the remaining symbols are like unerased. So sorry, from the overall local codes, it can transmit unerased information symbols. So not only from the overall local codes, here we will have to take into consideration the global parity also. So here, if you look at the global parity, here there is no problem. So we can actually aggregate this and transmit. So if you aggregate these two and transmit, so from this initial unaggregated transmissions, what we will get is we will get 3 symbols. And now if you are getting 2 more symbols, you will get a total 5 symbols. And from the fact that your code is of erasure, your code is of length 4, if you get 5 symbols, you will be able to recover all the symbols. So that is the idea. So here again, aggregation is possible within a type. And observe that the erasure patterns are not fully matching. Here the erasure patterns match only in the other locations, that is outside in the overwhelmed local codes and the global parity bits. So they have to match, but the other side did not match. So some observations. So what we can do is we can segregate these erasures. So depending upon the type of the erasure. One more observation is that just because all erasures are of same type doesn't mean that you can do aggregation. So you have to be a little bit careful there. So what we do is we can define an equivalence class within a type of within a set erasure within the erasures having type UV, and this equivalence class it has a property that any erasures within this equivalence class can be aggregated. There is no problem. So that has been defined in that paper. So I am not describing it here, but it can be done. And we also show that these equivalent classes have the same cardinality. So that is defined by beta of UV. So essentially, beta of UV of erasures can be combined together and looked upon. That is the idea. So this, we call this as the bunching factor beta. So this many erasures we can combine together and look at it separately. So now we will just describe the aggregation strategy and the analysis behind that. So again, first step is segregation into types, and within a type we will look at all equivalence classes and identify the set with the largest cardinality, or the largest or the equivalence class with the largest cardinality. So that is this MUV. It is so ML of UV is the size of each equivalence class, and MUV is the maximum value across these classes. Then what we do is we will aggregate symbols over this MUV for every type UV. That is the idea. So once you identify what is the maximum across all equivalence classes, we will do aggregation depending upon the type. Again, MUV is a random variable, so we have to do the expectation later. So CH is very easy. NH by NH minus S minus 3 plus 1. Now CHM is what is interesting. So let us describe CHM. I will skip that. So suppose if all local codes are unaffected, that means what you are essentially transmitting is only the symbols from the information bits from the local codes. So then if such an erasure, if such a type is there and MUV is non-zero, that is indicated by this indicator function, you will be transmitting KT symbols corresponding to this MUV. So if MUV is there, you will be transmitting KT. So MUV can be 0 also. So you have to put an indicator function to make sure that your analysis comes through correctly. In the second part is when there are erasures where local code is overwhelmed. So in this particular case, there are 2 summations here. again, the indicator has to be there because it can be 0 or it exists. So there is an indicator there. But the second part contains two parts. The first part, the first part is the transmission of information symbols of the local code which is not overwhelmed or which are unaffected. So if the unaffected symbols are directly transmitted, so you have to transmit that many number of symbols. That is why this M of UV multiplied by KT of I. And the remaining parts you can do the aggregation. Therefore, you will not have a multiplication with M of UV. Rather, you will aggregate together and you will transmit only that much number of information symbols. So that is the summation over KT of I belonging to support of U. If you remember, support of U indicates the list of codes that are overwhelmed. So these are the two things that we have to add up and find the CHM value. So again, finally, those rows which are not aggregated, we will be transmitting KT symbols because those are required for decoding. Those KT information symbols can be chosen appropriately and it can be transmitted. So in this calculation, what we observe is that we have two terms like one indicator function of MUV and there is an MUV term here. So while taking the expectation, we need two quantities. One is expected value of MUV and the second is the probability that MUV is greater than 1. So these are the two quantities of interest. And this entire problem can actually be converted into a combinatorial problem, which is like balls and bins problem, where each edge node is modeled as a ball, and all the erasures, all the possible erasures are modeled as bins, and you are effectively throwing any balls into NH choose S. So NH choose S is the total number of erasures that is possible. So out of NH, any S can go wrong. So NH choose S bins are there. So any balls are being thrown into it. And whenever there are more than one ball in a particular bin, then aggregation is possible. That is the idea. So again, one more thing that we can observe is that due to our aggregation strategy, some of these bins can be aggregated together and looked at together. So it is not like they are single bins, but you can actually merge these bins and take a look at it. So in our paper, we have found out these expressions for expectation value of MUV and probability of MUV greater than or equal to 1. I have not put it here, but we have some calculations. It is again not a very close form expression, but it's an iteratively you can evaluate it. Yeah, and it's slightly complex expression also, but this is possible, and then we can calculate CHM from that. So what is finally observed is that here we have established that there exists a trade-off between CHM and CEH. So what we observe is that as CEH is, if you can sacrifice a little bit on CEH, you can see a gain in CHM. So CHM continues to decrease if CEH increases, which was what we thought initially would have been happening. And through using the pyramid scheme, we are able to show that as T increases, that is, so T is the number of local codes. So this indicates the MDS code. So that is, there is no local code involved. Now here it is two local codes, T equal to 2, this is T equal to 3 and T equal to 4. So these are the points as the local codes increase, we are able to get a reduction in CHM, and so that communication costs can be adjusted, but you are at the same time sacrificing CH. So that is about pyramid scheme. So yeah, I would like to quickly spend some potential limitations and future directions. As Sir already told, you are working on a quantized gradient values. So once your gradient values is quantized, how does this quantization affect the convergence of the algorithm? So there are many interesting papers in that particular direction, and there are some, even in federated learning also there is a paper called as quantized federated learning, wherein which this particular topic is covered. So it is interesting, but it is possible. But there are some limitations. Another interesting problem is the lower bound on the achievable rate. So whatever we have shown in this graph is just achievable rate, and it can be improved. And we are sure that it can be improved because we have ourselves got some improvements for these schemes. But again, we don't know what is the best that is possible, because the aggregation strategy can be made as complex as possible, and you can get large amount of improvement. But again, there is no idea about the lower bound as such. What is the lower value for CHM? So that is a potential direction to look at. And what we have initially assumed is that all the helper nodes are accessible, which may not be true in a real life situation. Expecting all edge nodes to have accessibility to all helper nodes may not be a realistic assumption. It can be a realistic assumption provided you have some UAV kind of relay nodes, etc. But maybe there are other networks where in which this assumption has to be relaxed, and that itself, modeling that network itself is a potentially challenging aspect. Helper to master communication can be error prone. So yeah, that statement is, I think, clear. And yeah, this is the one major thing is that what I have described is a technique in which I need the full gradient. So in most of the applications, you really do not wait for the full gradient. Once you have some fraction of the gradient, you will do the update and then proceed. So under that setting, what is the what can be done? So how this can be extended under that setting? And finally, maybe if the edge nodes are not reliable, say there are some malicious data is involved, how to look at it. So these are just a potential future directions. Many of them I also don't know the answer, but then we can always take a look at it and try and find answers. So with that, I conclude my talk. Yeah, I think it is 4:55. If there are any questions, I would be glad to answer.
Thank you, Dr. Anup, for a wonderful talk. We can take a few questions now.
Yeah, and I know. Can you show that achievability curve again, that trade-off?
Yeah.
Yeah. So can't we do space sharing? Like, I mean, can't we do space sharing? Like, I mean, let's take like for a fraction of the gradients, I will use repetition, and for the remaining fraction, suppose I'm using like MTS coding. Then won't it be like joining those two corners a straight line?
Yeah, probably. Good suggestion. I think it should be doable, but I need to verify that.
Okay.
But we have not done that. Okay,
I mean, yeah. So basically, the interest is that, I mean, we would like to push the curve like towards the origin, right? I mean, we should both the things, right?
Bring it down. Yes.
Yeah.
Yeah, and this is not the latest curve. I think we have even with suitable improvements, we can bring it further down, but we have no idea about the lower bound.
Okay.
Yeah.
And yeah, one more thing is like, I mean, there is no interest in like removing the feedback. Is it like from so right now there is a feedback from master back to the helper node, right? There is not much motivation in removing that communication, right?
There is not much, because that communication, because generally we assume that the helper nodes are like they have the power to transmit, they have the bandwidth to transmit. Generally the edge nodes doesn't have that much capacity. So these helper nodes, we'll assume they have that much. So even that helper to master node, we can assume reliable communication itself. So that is why that was not looked up. But yeah.
And okay, yeah. Thank you.
Okay, thank you, Nikhil, for the question. Any other questions?
One question. When you're saying that events of erasure, is the erasure or the corruption of a symbol known with certainty, or is there some like difficulty in finding out which bit or which symbol is corrupted if you are having multiple copies for this? I'm referring to like, or coming from that perspective of, you know, like consensus problems in data storage.
Okay. Yeah, interesting. So here we are assuming it as erasures. So we have not considered it as errors. So what typically happens is that see, these edge nodes may not be active for all the time. So if a particular helper doesn't receive the communication at the scheduled time, he will consider that transmission as like erasure. So we have not looked at it as an as an erasure or an adversarial nature. But what we have looked at it as just either you receive the update from the edge node or you don't receive it at all. So that is the kind of approach that we have looked at. Does that answer the question? Or
yeah, in this context, yes. But
yes.
As a follow-up question, like, are there any studies or works in this area where you may have multiple copies of the symbols, and then you need to decide on which is the correct one, quote unquote correct?
So not to my knowledge, I don't know. I mean, at least I don't think I have seen anything like maybe 6 months back, but I am not sure. Sorry.
Okay, thank you.
Yeah, most likely no. That is my opinion. But yeah, it needs to be again checked.
Thanks.
Thank you for the question.
So you had one future direction where you said all edge nodes may not be connected to all helper nodes. So
Yes.
when they are not connected, you can do the same with, I mean, the same analysis might hold, but it might be weaker, right? In the sense that the erasures are more, I mean, for the other, you can assume a complete connectivity, but those might be erasures.
Yes,
So
yes,
you-
yes. Yeah, I mean, I didn't. Maybe who is the questionnaire? I didn't. It's fine. Yeah, thank you
Sorry?
for the question anyway. I mean, I didn't catch your name. I was
Oh,
looking
Vinay,
at.
Vinay.
Yeah. So thank you anyway. But yeah, you are correct. So we looked at it at that angle where we will consider like these erasures are like these are like sort of fixed erasures. So that way we can extend the scheme. But I think maybe we can. I don't know, but I have a feeling that maybe we can do something more intelligent. So this scheme can be extended. I'm not. It can be done. But whether we can improve on that or whether that other than anything other than a direct extension, that is what we have to closely look at. But what we found out problem is actually in describing the network itself, we had a problem. So how much erasures are connected to, how much helper nodes are connected to a particular edge node, in what manner it is arranged. So those things needs to be more carefully looked at. But yeah, as you told, this can be extended under that like trivial extension, assuming that they are fixed erasures, it can be done. But maybe something more can also be done. So that needs to be looked at.
Okay, thanks.
Okay, thank you. Okay. Yeah. Any other questions?
Are there any other questions? Okay, if there are no other questions, let's thank Dr. Anup again for for accepting our invitation and speaking at the CNI seminar series. Also, I'd like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. And you can also visit our website for more details. And I've already pasted the links in the chat box. The link to the recorded video will also be posted on our webpage. Thank you, everyone, and have a great evening.
Once again, thank you from my side for inviting me. Okay. It was a pleasure to talk. Thank you.